Hello, good afternoon, everyone. My name is JD, and a big welcome to NUS Enterprise. Thank you very much for braving the rain and coming here nonetheless. It's truly exciting to see such a strong mix of founders, researchers, investors, and ecosystem partners gathered here today for this session. The Ascent Series, which today's event is part of, is a curated lead up to NUS Enterprise's flagship A5X Global Innovation and Venture Summit happening this September. We will bring you closer to leaders who have already made the climb, individuals who have built through uncertainty, scaled breakthrough ideas, and navigated the realities of innovation at the highest level. Each session is designed to give you first-hand insights into what it takes to move from idea to impact, and today's speaker embodies that journey. We are honored to welcome Dr. Sara Hooker, one of the world's most influential voices in artificial intelligence. Sara was a research leader at Google DeepMind and was the VP of Research at Cohere. Today, she's the co-founder of Adaption Labs, and where she's building a new generation of AI systems that learn continuously and adapt in real time, evolve dynamically through interaction, challenging many of the assumptions driving the industry today. Adaption Labs also raised a 50 million seed round earlier this year, led by Emergence Capital, with participation from Mozilla Ventures and other investors. We're privileged to have Sara here today at NUS Enterprise to share her insights and perspectives on where AI may be heading next. Please join me in giving Sara a warm welcome.
It's lovely to be here. Thank you so much for the warm welcome. Let me see. Oh, perfect. Oh, this is lovely. So I think I have probably 30, 40 minutes with all of you, and then we should get into the fun part and do the discussion. So I was thinking, what should I speak about with this group? I tend to be one of those people who puts together slides at the last minute. The good thing is I had a very long flight yesterday, 17 hours. So I knew I had all the reminders on my calendar, got to do the slides. I actually have a few presentations this week. So I did what many perhaps sensible people would do to begin. I asked ChatGPT, I need an opening slide that speaks to why we need adaptive intelligence. The result was this. It's a bit bombastic. It's got a bit of flair. I think it's got clearly Darwinian influence with the lizard, so a little bit of like evolution there. But it is interesting. So I said, okay, let me give it another go. I said, okay, I need an intro slide for myself. So for reference point, and by the way, that was a lovely introduction, but for reference point, this is my normally intro slide. I've done a lot of work at the frontier. One of the things that drives me is research at the edge of what's possible that also translates to real-world impact. And then this was a slide returned. There's only one slight problem. um, and yeah, I guess I could have given thumbs down, but it would have taken a while. Or I could have spent a long time prompting it. And I think that probably captures what many people feel about current AI, which is that we kind of ship the same model to everyone, and then we turn people into elevated prompt engineers. They have to do a lot of acrobatics around the model to make it work for them. I think intuitively, the other thing that drives me a lot is that by shipping the same model, we also end up spending a lot of unnecessary compute. We treat every problem as if it demands the same. And I think there's hard and easy problems, but we should be much more efficient about it. So these are now my slides, by the way. I gave up. But the cost of this static intelligence is, I would say, three. I think it really doesn't do a good job at capturing the complexity of our world as we move towards systems that have that real-world impact. But also, you just spend a lot of resources trying to both wrangle it and make it work for you. And it's one size fits all. So today, I actually would suggest there's a better way forward. But I'm not going to tell you, I'll try and share why I think this was the right time to work on this problem. And I think there's two drivers. So whenever you work on a problem, you have to decide, well, time is valuable. Why do I think this is, both the right problem and the right time? And so I'll share like what's driven me to work on continuous intelligence now. And I'll propose two things, and you can tell me if you're convinced by the end. One is that the era of blindly scaling is over. So I think that in many ways, this means all bets are off, because it means that the recipe and the innovation matters again. The second is the next era of intelligence will be defined by the cost of adaptability. And so whoever can do that most efficiently will determine who gets to shape. And then I think that the third thing, which is very important, I think the whole stack has to be adaptable. One of our key visions is that everything from data through interface should change based on your task. So let's start. This will be fun. So how did we get here? So how did I get to my opening slide and maybe the limits of scaling? So I was just having this great conversation about what drives someone to write. And I say, you know, I have no time anymore, so I only write when I'm extremely grumpy about something. And I feel like it has to be out in the world. So this was my very grumpy paper. So feel free to read the entire piece, which is really about like why we're in a slow death of scaling stage. And in some ways, this is kind of a contrarian view, because most of the last decade and most of my role, you know, both at different frontier labs, has been how do you leverage compute in the most effective way to scale your model? And how do you build the biggest model? And actually, there's a few rarefied places where there's both the technical know-how and the compute to do it. And in fact, that's really what we did very well, right, with scale. And this is across tasks, so it's domain irrespective, multimodal, the same trends. It's also data set and model size. And so we've really been very obsessed with this idea of scaling. This is captured by Richard Sutton as the bitter lesson. So it's kind of a punch to our egos as computer scientists, because what he's saying is your ideas only matter if they can scale. And the only thing that matters in the long run is the leveraging of compute. And this is in some ways, this was the Bible. Actually, like a very important computer scientist researcher called Michael Jordan, not the basketball player, the researcher at Berkeley, he said, I can't think anymore without holding a piece of metal, which is very interesting, right? It kind of reflects how much we've adhered to this. So is Sutton right? Who thinks he's right? Hands up. He won a Turing Award. So someone, I mean, I think it's very reasonable to say he's right. Yeah, who thinks that he's right? Oh, excellent. Yes, very good. Excellent, nice. Who else? Very good, yes. Very good, excellent. Yeah, I think that there's actually very many rooms where people really do think he's right. And in some ways, it's really important we think about this question of whether he's right, because it's impacted everything. So we have CAP saying GPU poor. We have shifted contributions from academia to industry. Like there's very few labs where you can do this type of work. It's determined who gets to participate and who doesn't. And it's made acquiring compute a critical necessity. And I think what's interesting, it's even led to adoptions of policy. Like the model is considered unsafe if it's above a certain number of flops or size. It's also led to a handful of providers determining who gets to shape AI. So yeah, I think if we polled this audience, I think people would have the same names for, for some of these company placeholders. Some would differ, but it's very interesting. I think it's a small set that's determined. So it's a very worthwhile question to ask, is Sutton right? Is scaling all that matters? So for the courageous souls who put up their hands, there's actually a lot of evidence that suggests that you are right and Sutton is right. Like if you look at the last decade, most empirical evidence is in Sutton's favor. So is scaling necessary? It turns out like it allows for very different regimes of capacity to emerge. Research has shown that you can only get certain types of performance on models of a certain size. And it requires larger models to take advantage of things like instruction fine-tuning. It's very hard to even enable tool use on smaller models. And all this, it's interesting, suggests, and certainly if you look at things like ML Marina, I do have another grumpy paper about that, but if you just, if you're taking it as a relative index, you see larger models are ranked higher. So the first model on the leaderboard with known published parameters is Kimi, which is 1 trillion parameters, right? But before that was DeepSeek. These are some of the largest models. So all this is kind of saying the people who raised the hand are, there's empirical evidence to date supports exactly that position. And frankly, it's still a widely favored approach for a few reasons. So it's more de-risked. So typically, it's much easier to say to justify throwing more compute at the problem than to do something that deviates with the recipe. Secondly, it fits very handily into quarterly industry planning cycles. So this is very, when people are saying, well, what can we do this year to catch up? It tends to be a very easy proposal. Also, I think a lot of people raise capital based upon saying we need this for compute. So it's a bit awkward to then turn around afterwards and say, no, 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 we actually don't need the compute. So I think this justifies a certain narrative. But let me propose the contrarian view. Let's have a bit of fun today. So what's the contrarian view? One is, I think that it's a very logical one. So applying, building bigger and bigger models only makes sense if the rate of return is positive for compute. Like in some ways, you shouldn't spend compute on something that has decreasing returns because it's a very expensive asset. And I think there's increasing evidence that there is a very poor rate of return. So we see over time that models of the same size have been getting far more performant. So the recipe matters more, not just the size. We have more evidence that small models frequently outperform larger ones. So in this case, we have like models over 13B that outperform all models over 13B, which is the gray, the larger ones, that underperform the best daily model. And this is actually quite frequent now. So we're able to both train and use optimization techniques, which are lower compute but produce better models. And there's also just very good evidence that deep neural networks in particular are super inefficient learners. So beyond a certain size, you're really trying to squeak out diminishing returns. We know that, for example, most of the weights in a deep neural network are correlated, so they end up representing very similar things. So for example, this is a very nice classic paper. You can use a small set of weights to predict 95% of weights. But you can also get rid of most weights when you're finished training, which kind of suggests that you only need it for like good optimization, but you don't really need models to be that big. It kind of suggests that we just don't have a good way of training, which is fun. And also we know that high quality data drastically reduces the amount of compute. So you can get away with a lot more bang for your buck if you invest in the data. We also know that because like our deep neural networks are average learners, they just learn based on average error. It means that very common examples are learned very early in training, just a few steps in. It's very fascinating. Most of training, most compute is spent learning very rare examples, and we pay a lot for it. So if you're training a big model for like 3 months, 1 month plus, you're basically spending the majority, 85% of that time, learning very infrequent features, which is crazy. This is also, actually a lot of our work was on establishing this relationship between capacity and the long tail, but you can see this in different ways. So when you increase the size of the model, you gain performance on those rare artifacts. And there's diminishing returns. So this is a quaint example from the very, very far past, Inception v3 versus v4. But we also see it with current models. So you can double, in these old school models, you would double the size of the weights and you would get 2 percentage points gain in accuracy. But we kind of also see it in the reception of recent models. So I'll be a bit cheeky now, but like, for example, when GPT 4.5 was released, a lot of the consensus was this degraded capabilities, but didn't add much, but it was massive. So it was so costly but to actually serve. And then I think the decision was taken by OpenAI itself not to keep serving because it was very high cost. The same, I'll be cheeky, I think is happening with Opus right now. So it's very good at that final slice of tasks, but to be honest, you don't want to serve that model every day for most tasks. And that's really interesting because all this is basically saying transformers are saturated, at least size-wise. And so that's interesting because what it really suggests is innovation is no longer in pre-training, it's actually in the recipe. So what's the way forward? What's the era of adaption and why this is an interesting problem? I think this is about, where do we end up? So I may have convinced you that we're now in a period of decreasing returns for compute. So we'll see. We can do a poll afterwards. I see the questions. But regardless of whether I've convinced you that transformers are saturated, I hope I've convinced you that, hey, this is a very expensive way to learn about the world. We're paying a lot to learn about the long tail. And that begs the question of what comes next. So if scaling is slowly dying, and particularly scaling size, what is our biggest lever of progress? So most of computer science history has been centered around the algorithm. So 1950s, modern computer science history starts, and all of it has been about the algorithm. It's like, what is the model? And even that's how it's framed. How do we impart to a machine skills reserved for humans? And what's interesting is that we're in an interesting time where tools for optimization is finding new spaces. So I think what's happening in the data space is super interesting and really not talked about enough. I'll share a little bit, but I think this is powerful because for the first time, this is an optimizable space because the cost of generating data is very cheap, which means that you can do things in the data space that previously you would see as like, that's too unwieldy to optimize. And then I also think we're very much moving towards an era where the most intelligent model will be one that interacts, and so it will be a system. That's very profound because it changes what researchers should care about. They have to care about the interface again. And that's very interesting, actually. The rate of return is much higher for compute in things like post-training, alignment, adaptive compute, co-design with hardware. What that means is quite powerful because it opens up the era of research again. So before you had these concentrated labs which had disproportionate GPUs, and if all that matters is pre-training and all that matters is model size, it's very unlikely that spaces outside of that can do things that are interesting. But now what matters is much more the recipe and the interaction of who does serving, algorithm design, and also interface design very well. And these are typically functions which are very separate at most big companies. But it's actually quite interesting. There's a whole innovation there. So what would I say? I think this means all bets are off. I think it's fun in some ways for us at this present moment to think about what is the next era of intelligence. I'll share a little bit of what I think the highest leverage bets are, and then we should start opening up for discussion because I think that that's always the most fun part to see where people disagree or agree. One is efficiency of interaction matters. I think deeply that if you believe that the most intelligent model would be one that interacts, the efficiency of how a model updates its behavior is going to determine who gets to shape adaptation. And so we care a lot about efficiency. We think that a model behavior should change real time, and a user should be able to see that. So when I ask for a slide, I should be able to not have to then write a million prompts to get a change that I desire. But secondly, I think size of model does not matter anymore, candidly. I don't think we're going to see any frontier lab 4x the size of their model over the next year. I think that era is over because typically what conditions most of whether you can scale something is like the type of architecture, and I think transformers to some degree are very saturated. And then I think continuous learning very much matters, especially as we have long time horizon tasks. It matters more. Can you update your behavior in between steps? Otherwise, you spend a lot of compute doing these very expensive rollouts. So what do we think? And I think at Adaption are the highest leverage problems. And maybe this is helpful for many in terms of thinking. So we are building intelligence that continuously adapts. And like a lot of our work is on these three pillars. So I'm happy to talk if there's interest or if people want to talk more after the talk. If any of these interest you, super happy to talk a little bit more. But our belief is the whole stack should be adaptable. Like when you have a different task, everything should change from the type of data to the model itself to actually the interface. It should be dynamic. And this is a fundamental shift. You go from a monolithic model that's shipped the same way to everyone to something that's fully adaptable. And I will say why this is important. I mentioned adaptive data is one of the things that's changing. It's worth asking why. So one, optimizing the data space bends scaling rules. But it's also the first time that it is cheap enough to steer in the data space. So historically, ML researchers have treated data as fixed, and so something to be worked around rather than something that they can control. For a few reasons. One, typically, traditionally, it's very expensive to collect data, but it's also, once you've annotated data or added additional dimensions to it, you can't change your taxonomy. It's too expensive, which is it's very interesting because we see this with how long we were stuck with terrible academic data sets as our measure of progress. So I think we look back on these fondly, but there were so many mistakes in the original annotation, but we stuck with them because it was too expensive to collect something new. And actually, a lot of AI in general assumes that the cost is super high. We premise everything on being sampled at random from the real world, and that that's representative of the real world. But now, for the first time, I think we're in one of the most important paradigm shifts. So advances in data make it much easier to imagine this space as malleable. And what that changes is very interesting because it allows you to target parts of the distribution you want. So before we had to sample at random, hope for the best, but now there's no reason you can't target parts of the distribution and aim for your long tail. And this also changes the efficiency of your learning algorithm. I think we did a lot of work on this over the last few years, but I call this almost like a version of active inheritance. You can choose what traits you want to inherit, and you can target parts of the data distribution that you want. And I think this is very important because it also increases the speed of iteration for many fields. We did this as our first pillar. So one of our first releases was adaptive data. So anyone can steer. You're welcome to go play with it. But the idea is you should be able to specify any objective freeform, and then the whole data set is optimized towards it. But even the algorithms adapt the way that the model is transformed to make it visible for AI systems. And this is very cool. So I actually think since last week we're at 25 million. So we just released this 4 weeks ago, which is very cool. But we show we have 242 languages and 82% improvements in accuracy. And I think this is very powerful because our goal is to make it very fast. You should be able to generate data on the fly for the type of problem that you want. The second core problem or area of leverage that I see is that you should be able to change the model layer. There's a few ideas here. I'll just list them of what I think is interesting. One is this idea adaptive compute. You shouldn't be paying the same amount for different types of problems. We tend to be very good at that at humans. We discard information very easily. We actually spend very little time on easy problems, and we're willing to spend considerable time on hard ones. This is very important that we switch towards adaptive compute. It requires changes to our systems. It requires serving efficiently and placing more compute on test time, which is very interesting. The second is, if you care about real-time adaptation, you have to care about gradient-free learning. How do you condition model behavior without needing training? And so this is a key area of focus for us. And then I also think it's very good to optimize explicitly for adaption. So a lot of post-training alignment techniques, but also fundamentally techniques about how you ensemble weights on the fly. I think these are very powerful. These are key areas that are very interesting, and long horizon tasks in particular. We just shared, and I'll just share this, because I actually think most fun for us are tasks outside of coding. I think this is where the meat of the problem lies right now. So how do you instill non-verifiable tasks like indicators of progress, and how do you steer? So actually, we released our first work in this direction of how do you automatically learn spaces and impart model behavior. We released something in AutoScientist. So now my time zones are catching up with me. I think it was day before yesterday. It was the day I flew. So maybe it was yesterday in San Francisco. But it was really nice, the reception. I think we got a bunch of coverage for it. And I think this resonated because what AutoScientist does is starts to co-optimize the learning process. One of the biggest hurdles is that outside of frontier labs, people have not had much success training frontier models. And so what's interesting is to make that process much more efficient and to co-optimize the whole process from data to also proposing how to learn, and also really learning from the data what's the appropriate way of training. This is quite powerful. I actually think what is very cool about it is it outperformed our own research staff. So I attribute this, our research staff was very used to working on a certain family of models. Typically in frontier labs, you make certain architecture choices and you squeeze so much out of that. And it depends on your hardware and also your architecture, things like that. What's interesting is that because we ran AutoScientist around so many different types of models, the goal was to make it generalizable. Most research staff, even at AI labs, is very used to their priors for that. And so AutoScientists actually outperform the human configured training when you consider this massive pool of models, because you can imagine they're all so different and they all have to be coerced in certain ways. And so for me, this is very much evidence of how do we accelerate research itself with basically the dynamics of understanding the task and also understanding the mapping to different types of models. Very interesting. And I think what's also nice is that this gives predictable gains. So it allows people outside of labs to trust that it won't be a waste of time to own their own AI. I think that this leads us to where we think is important next, which is that you should just have continuous self-improvement, and you should be continuously learning from your environments. This starts with how do you just adjust, but it also means like eventually you should even need to bring data to the problem. So what are my parting thoughts before we open up and start engaging? One is that I like this quote. This is from John Gardner. He says, "What we have before us are some breathtaking opportunities disguised as insoluble problems." So, okay, transformer is saturated. Pre-training is, I think, more and more a data problem, not a scaling problem of data model size. But I also think we're in this remarkable time. So modern computer science has only existed for 75 years. And I think when you think about that, it really hits home how interesting the problems that we have right now are. And also the expressiveness of the search space that we have. So much is shifting to this expressive test time scaling. How do we combine these models in interesting ways? And it's shifting to the system and interaction. I think there's plenty of examples to tell us that the future is not deep neural networks. So, we have examples like our own intelligence, which is much more adaptive and is much more efficient. It basically runs in the equivalent of an electric shaver. And there's key design choices to embed efficiency. One is that we tend to discard a lot of information. We have log scale vision, so we don't absorb most changes unless they're notable. We also tend to optimize for certain types of tasks. So typically, it's very much easier for you to walk and talk than it is for you to walk and read, for example. And there's also very clear examples of what's wrong with our current intelligence, right? With deep neural networks, we basically treat all examples the same. We don't really have adaptive compute in a meaningful way. We also do global updates, which means we erase most information. We don't have nimble ways of imparting continuous learning. And I think the third is we optimize for the average. So it costs us a lot to learn the rare. And those are all very fun problems to think about, but also clearly our present status quo is not the future status quo. So I think that's the fun part for both institutions like really universities all over the world, but also for people working at the cutting edge of innovation. These are very powerful questions because they're going to determine who gets to shape AI. And I would say, I don't know, but I think compute is probably the least interesting approach to the problem, especially if it's just scaling size. I think there's very interesting, better rates for return in post-training, test time scaling. But those require more thought as well into how they're leveraged into a harness for learning. So yeah, I think this is a little bit of what we're working on, but maybe I'll just open up. I think we should open up for discussion. I did ask for one last slide. I thought this one was better. I thought it was kind of lovely. So there, who knows? It gets a little bit better. But maybe we can open up. Yep, go ahead.
Thank you, Sarah, for the insightful and thought-provoking sharing. So we actually did poll the audience for some questions before as they actually sign up for this event. And I do have a list of different questions, and maybe you can help kind of answer them before we open up to the floor. So from Will, many companies are now using AI, but some may actually, maybe only some may become genuinely AI adaptive organizations. What do you think separates the two?
I think it's very hard to own AI right now outside of frontier labs. I mean, if you think about it, I think fine-tuning techniques which are about building your own AI have, I would argue, largely failed outside of frontier labs. I think it's considered people don't have the right data, or once they do, they find it too cumbersome, and then they get the signal and they only have data for what they want, so there's forgetting of everything else. So I think it's understandable that there's been this friction. I think what you see instead in most companies is prompt scaffolding, right? So there's a very multi-layered set of prompts that are hand curated. And what's interesting is that that is people who've tried to own their own AI, felt deeply unsatisfied, and returned to being prompt engineers. So you have to, I think that that pain point has to be addressed before people will meaningfully invest in like how do they shape and become, have their own vertical specific AI. And there's two things for that. One, it has to be much easier for people to get data in a meaningful way that's optimized for frontier labs. I think most frontier labs, actually, a lot of the levers are very powerful data recipes. And so I think that has to be true here. And the second thing is that I do think it has to be much faster. That companies see attempt to shape AI translating into something that is actually customized. Otherwise, prompt engineering often takes hours and hours and hours of tweaking and seeing a keyword, but people do it because they can see the before and after immediately. That's the root. So it feels much more exciting because they feel control, and that control is what has to be imported from really the technical tools that we give people.
See. Well, second question from Selwyn. Where do you think we are today on world models? And do you see adaptive AI agents and world models converging over the next few years?
So I think world models matter because we're moving towards an era of interaction, right? And so world models means different things to different people, but largely for me, I think it's more how a model interacts with the world matters. And that means that we have to think about long-term horizon tasks, which is important, but also I also think updating model behavior as you go is important. So it's very related to what I think is core to adaptive AI, because why do you care about continuous learning, for example? Like, why has this come back into vogue? Which I think is it's become something that people, been a very active field, but it's become urgent. The reason why you care is that now most tasks are going to be long task horizon that are meaningful. And so if you naively apply a model the whole way throughout a task, the likelihood that you're going to end up at a good solution is very low. Typically, the way that's overcome right now is people do so many rollouts and they're trying to saturate the search space, but that's a very expensive way to do things. So having a way that you update model behavior every step of the way with every interaction becomes critical. And that is continuous learning, like how you do it over steps. And so world models and this emphasis on continuous learning or ability to update behavior has become very important.
Great. Third question. Looking ahead, where do you see the bigger opportunity? Digital AI, where systems adapt inside software workflows, or physical AI, where systems adapt in the real world? I guess.
Yeah, I mean, physical AI is it's, yes, that's like the holy grail. There's an interesting, so we don't work on physical AI, just let me put a disclaimer. I think the robotics is very difficult. So typically, what defines a difficult problem? Typically, there's two things: the cost of experimentation, so how quickly it takes you to get to a result, and the gap between where you test a model and where you end up deploying it. The bigger that gap, the harder the problem is. Robotics has both on steroids. So this first problem of how expensive it is, I think the big question right now is form factor for robotics. Are you doing a humanoid robot? Are you doing a little cute delivery car? Like, both of those have costs. You're deploying hardware, which means you're definitely in a production logistics setting. And that's even before you get your first signal of failure or success. The second, which is also on steroids there, is that you have where you're testing, you're simulating your algorithm, and then where you're deploying. And robotics has that issue too, because typically you test in computers and you try and deploy to your cute little robot. And so that gap means definitely it's much harder. I think so. You will probably see much more digital adaptation first. And I think typically the way people overcome robotics is by sheer collection of data. You're just betting heavily that you are the first to collect enough data to learn and to bridge that gap. It's a more difficult. I think roboticists there's a divide there. And I think that's what makes it interesting and high potential, but it also means that we're further behind there.
Great. Alex asked the question: in the world where the largest AI companies have enormous compute and distribution advantages, how can smaller AI companies like startups from Singapore compete meaningfully?
Well, I think my talk was probably a positive message there. Compute still matters. I'm not going to minimize that. I think it matters in different ways. So, like compute, the rate of return now for inference and the rate of return for post-training is just way more lucrative than any compute that could be spent for pre-training. But it still matters. But why the dynamics of that compute are different. So typically, post-training compute and test time compute doesn't have to be co-located the same way that pre-training does. That tends to be a massive advantage because you can leverage different data centers. You can also have redundancy. So some hardware can fail and you'll still be okay. This all means that the space for innovation is a bit wider. Training compute, typically you need it all co-located. You need to book hardware for a very prolonged period of time. So this type of compute need is a lot more refreshing. It's more fun. You're going to have much more dynamics of who has the best idea wins. And that's a good thing. That's why you also see so many bets on really companies who are betting on the next era of intelligence that are emerging now, because there's a feeling that, hey, this is the dynamics of just being able to place a lot of compute in the same data center no longer play out in the type of outsized way. So I think this is a good era to be in.
Great. Sunil asks, if future AI systems are adaptive, how important is the global south? Its languages, users, constraints, and data environments to build models that actually understand the world.
Very right. So language is important because typically it's both a way we connect with each other, but it's also a vehicle of utility, which I don't think gets talked about as much, right? So when you order a pizza, you want a pizza to show up at your door, and language is a very important utilitarian vehicle of value. And I think that a lot of my uh, career has been how do you expand languages in such a way that AI serves many more contexts. And so it is critical. So typically, language is also fun because it's one of the most difficult, it's a good example of very quick impact, but has all the difficulty constraints of a very complex adaptation problem because you may have very big disparities in data. You have to do it efficiently, but also it's very clear when you're wrong, right? I think people are very good judge of what matches what they expect or not.
Achala asks, what would adaptive AI change in traditional industries such as pharmaceutical manufacturing, where the environment's complex, regulated, and operationally constrained? Do you see that impacting us?
I think those are the industries where AI has still largely failed, right? There's a fantastic MIT report which basically shows the last mile performance of AI. That you can roll it out for your customer service, but for meaningful long horizon tasks, it's largely not delivered. And that's the exact type of complex problem that needs adaptation. Typically, for example, you may have differing standards between countries. You may actually have to different database structures. And I think this is all examples where you need much more malleable AI that can change.
Well, I've picked 6 questions from the audience from before. Any brave souls who would like to actually ask the questions directly to Sarah?
Excellent. Nice. Well done. Great. Yes, we should have. This is good.
Hi, thanks for the discussion. We built virtual cells for biomanufacturing, and I was pretty interested in the part that you said oversampling synthetic data set is a good part because in our industry, data is expensive to get and they're sparse. Can you explain a bit more on that? Thank you.
Yeah, I mean, I think that a lot of it is how do you leverage the limited number of samples you can get from the real distribution, and how do you target that distribution and better represent it? And the two technical challenges are important. One is you need diversity still, and it needs to be representative of your real world distribution. And typically, a lot of the techniques that have been within Frontier Labs are doing both. So, how do you leverage a small sample and then squeeze that to both get more diversity, but also still stay close to that part of the distribution? But it's very powerful.
Okay, thank you.
Hi, Sarah. My name is Yao. I've been working building and marketing tech products in the last 10 years. The full stack adaptive products AI model is really interesting. I'm wondering whether the front end adaption is reliant on the back end model adaption. And I'm asking this question because I'm also thinking of this placeholder company A to C and whether they can build an adaptive front end without changing their back end models?
Yeah, that's such a good question. I love that. I think they're very intertwined. I think so. Why does interface matter? I think it matters so much because, so think about code, why it accelerated so much. So uh, it really accelerated because also of the interface. We basically used interfaces that really we as engineers used anyways. And so we were very willing to give very granular feedback along the way. And the way we gave feedback was way more powerful than just thumbs up, thumbs down. That doesn't, I think all other tasks have been relegated to thumbs up, thumbs down. And I think that's super interesting because for me, what it means is you have to care about dynamically changing the interface because you have to care about how people are able to shape AI. And if you care about that, people have different interfaces they use for different tasks. And to just do a model is not sufficient. And also, if you care about real-time changes to model, you need that model to be able to respond based on how someone interacts with an interface. So yeah, I think it's crucial to co-design both. I actually think what's interesting is you look at companies like Cursor, they were very much an interface API wrapper first, and now they're really investing in their core tech. And it's really interesting. That's come fairly late, but that you can see the difference already in how they're trying to make up for that ground. Imagine if you have that combination from the get-go. So like even at Adaption, we care for about design from day one, and we care about this idea of how do you very rapidly, dynamically change interfaces, which is very powerful. Yeah.
Thank you. So the interface is part of the feedback loop.
Yes. Yes, it has to be, I think. Yeah.
Got it. Thank you.
Sara, thank you for the inspiring talk. So actually to achieve the adaptation, I think we can have two ways. One way is like we update the model parameters, right? But
Yes.
another way, actually, we can also use actually the memory.
Yeah.
And then the memory and the model can interact with each other. So what is your opinion? What will be actually the future for
Oh, this
adaptation?
is such a good question. I love this question. This is the core question, which is going to define, by the way, who shapes the best recipes. So I think too many companies and labs are fully betting on one or the other. For example, I think for me, entirely parametric solutions it's very difficult to imagine continuous learning within that framework because our stable optimizers are global, and so you have a lot of instability if you're trying to introduce new information. However, it's certainly true that innovation and post-training and making a model more flexible and overcoming some of that is going to be very powerful. The combination is important. I said this example of a breakfast. We were having a meeting, actually, which was very interesting. Someone said to me, somehow it came up, we were talking about not being geographically orientated. And I'm terrible at geography. Like, I couldn't walk from here to another building without Google Maps. And what's interesting is that I was saying, I think I actually have a relatively good sense of direction. I just don't care about that information. It's not the type of information I want to store and be obsessed with every day. And it's because I know I can store it on my phone. And this is exactly the same question, which is what should you store in your brain versus what should you store externally?
Yeah.
And the balance of that, who gets that right and who optimizes for both in a powerful way? Because I actually think it's also about the nature of the information and learning that as a meta problem. What do you leverage for different stores that is the crux of it? So this is one of the most important questions for continuous learning. And actually, who does well at this question is going to determine a lot of progress. So it's a very good question.
Yeah, I also have the same opinion. Yeah, thank you.
Nice. Yeah.
Hi, I'm Dianbo. I work on AI scientist. So you mentioned you recently released something called AutoScientist.
So you work on AI scientists?
Yes, yeah.
Oh, we should talk.
Yeah, we chat. So
Okay.
recently we found one problem. We compare many AI scientists published, including the one from Google,
Yeah.
with that one line code from under capacity auto research.
Yeah.
And actually, very few people beat that one line of code. So what's your opinion on that?
Yeah, I actually think so. If I look at all these proposals for AI scientists, one of the things that I think is quite difficult is that they're too unbounded. So one of the reasons I think AutoScientist we got such great results is we basically adapted the data beforehand, right? So most automatic AI scientists have massive variance because they basically abstract away the data. So they're only focusing on the hypothesis, and then they assume there's data there, but they don't control for the quality. And so I think that that is very difficult to do. And actually, one of the reasons adaptive data was our first pillar is that we knew that jointly optimizing was so crucial. Because when you jointly optimize the data shaping and the model shaping at the same time, you get very good results. So I think what we'll see is the end-to-end matters a lot, and doing that long horizon both across the entire task tends to actually be quite important, which is interesting. So I'm not surprised that you're seeing equivalence, because I think those versions of the problem, they're interjecting a stage of the life cycle where it's quite high variance, the results. It's quite interesting. I don't know if that's what you have observed too, but I actually think it's very important to optimize across the problem.
That's right. Okay. Thank you
Yeah.
so much.
Yeah, that's excellent. But we should talk after. This is fun. Yeah.
Hello, my name is Rafa. I'm a student at Cornell. And I was wondering, you talked a lot about non-verifiable outcomes on one
Yeah.
slide. So I was just wondering, what's your vision on gathering data on this sort of non-verifiable tasks that I think humans do every single day, and there's no closed loop feedback sort of system in place as of now?
Yeah, I actually think a lot of that's related to why we think the interface should be dynamic. I think it's very hard to get feedback if the only lever people have is binary. And actually, I think that there's various different approaches to this, right? One, which is the browser agent approach, is the idea that, okay, um, if we can basically enable agents going across the internet, we can try and gain an understanding of these tasks. But I think there's an issue there, which is typically websites are so different for the same task, you don't get enough. You need some stability in signal. And so that's why I think it's much more interesting to start to imagine, how do we dynamically change interfaces and also control the type of building blocks so that we get a better signal about how people traverse tasks, because that is pretty crucial. I think that who does that well in a way that is useful to people. So I always say, like, so you can have the best idea, but unless someone feels something about it, it's very unlikely that it will have a real world impact. And this is one of those perfect examples. So coding really accelerated when it was useful to engineers, when they were just about willing to like spend hours giving feedback because they're like, oh, I see something here. This is actually making my life a bit better. And that same dynamic has to happen outside. We see that the areas of best progress are design and coding. And frankly, it's because designers are willing to give a lot of feedback. They're very opinionated about what is good and what is not good. And tooling that has enabled that and interfaces that have enabled that have really been really beneficial for designers. And so I also think about that a lot. Like, what actually, it's not just about what you build, but it's how people feel about it. And those dynamic interfaces have to be useful. Yeah, but that's a good question. I don't know. What do you think? Are you working on it?
No.
Okay. Yeah, more people should. I think, it's interesting. For the first time, the purview of a computer scientist also has to be the interface. And previously, that was relegated more to HCI, which is an important subfield. But now, if you think you're going to be working on the best system in the world, you better care about interface, which is very different. And I think who's slow to catch up there and understand that will not be producing the best model.
Yeah. Just like one follow-up, if that's possible.
Oh, that's cheeky. Okay, go for it.
I was wondering, so you mentioned, like, let's say coding and design. Is there any other space where you see where people might be having a really like benefit from it and willing to give feedback?
It's interesting. If you look at the top use cases of models, I think it's interesting. I think that in general, interfaces could be way better for people who are doing writing or coaching of different types. But to be honest, I think it's a sharp cliff after those two. I mean, I'm curious for the audience. Do you think interfaces are as good outside of those two? I think for the most part, we're relegated to a chat interface after that. Yeah, which is pretty interesting, right? Because it speaks to how wide that space is open. Yeah.
Thank you so much.
Yeah, of course.
My question is, let's say you achieve the holy grail of adaptive AI. Will it work in a similar way to how the human or the animal like brain works?
Oh, it's such a good question. Okay, so typically, so I actually think yes. I don't think it will, and I think that's a good thing. Meaning, our intelligence is very particular, right? It's very tribal. We all agree to be here at a certain time, so we all show up. Typically, what drives us as humans is the respect of other humans. Our intelligence is not actually about a single intelligence; it's collective. That's a lot of. We're able to harness collective uh, desire for each other's respects in a very powerful way. And actually, I think it's okay if you design AI that does not that is differing from that. And we already see this, right? I think there's some tasks that we are much better at, or that models are much better at already. But it would be surprising if we were. For example, mathematics, it really doesn't surprise me that models are going to be better there, right? Because we're not very good at sequential processing or long task horizon, which requires precision. We're very good at basically efficiently discarding a lot of information. And we're very good at our desire for respect, meaning that we align extremely quickly on the same consensus. I think COVID is a great example of this, right? As a global population, we all decided to lock down. The speed at which we did a global update was incredible. And that just shows like so much of our intelligence is collective organization. And I think it's okay if there's different aspects to this. So I think it's a very good question. Yeah. I also don't think adaptive AI will either. I think that it's kind of like the question about AGI, what will happen when it's here? Typically, it's not a binary. It's probably already happening in some ways. And so, yeah, it is interesting to think about though.
Maybe a last question.
So, hi, Sarah. Thanks for the wonderful talk. I wanted to ask about recipes. One sort of inference I got out of your talk was the era of compute is over and now recipes matter a lot more. And I wanted to ask, it's a two-part question. A is, were large models sort of like an important evil endpoint so that we can distill those information into smaller models? And B, where's the prior for new recipes coming from? Is it just sort of spanning archive every day, seeing what works, what does not work? Or how are you thinking about updating your priors, and where does this sort of clever recipes come from?
Yeah, I think to the first question, yes, certainly distillation from larger models has very much been beneficial. I think that's, but I think up to a point. So if you look at like a 300 billion parameter model versus a 400 billion parameter, the difference in distillation benefits are more marginal. So I think we've hit that limit. So no one is going to 4x the size of that model because it's just not worth it, even from a distillation point of view, which suggests that scale, of course, matters, but we're at the limit of what we can do with transformers. So I think that's the answer to the first. The second is quite interesting, like where do you get the idea for the recipe? So a sign that there's no clear answers to the space, frankly, is how many different agentic harnesses have been proposed and the lack of consensus about which one matters. So even the Claude code leak didn't decide things. I think it actually just surprised people that they don't really know the answer either. So I think it's very interesting because all that suggests that the recipe is unbounded again, right? And that's a facet of two things. Like, why is that happening now? One is that if interaction matters, your search space is a lot bigger. So the question of how to do that, I think, is undecided. I think for us, the critical thing is we really believe it has to be fast because the faster your model can update, the faster it can explore the environment. So my co-founder, Sudeep, he is a systems person. So he developed pathways for Gemini. We think that most of the times who designs a model and who serves it are two separate, completely different functions. And my function would be building the best model, and then we almost toss it over to serving, and they try and make it efficient. But for us, those are one and the same. We're co-designing because we think that's so critical to who will be able to shape adaptation is going to be who can make it very efficient to update learning. And I think that matters. But I think that, again, there's going to be various components that matter. And that's why I think the whole stack has to matter, not just the algorithm. Yeah.
Well, Sarah will be available for networking right after this. But I do have one last question.
Oh, cheeky. Okay, nice. Go ahead. Go ahead.
Which I think is quite relevant to what was asked earlier about actually meta skills. So Michaela says or asks, as AI systems become more capable and adaptive, what human meta skills become more important rather than less?
So I think it's so funny. I feel like we've covered so many topics we were just talking about before this talk, but I actually think what matters is two things. I think that the idea of how do you intervene in an efficient way matters a lot. So that's one. So, when can you tell if something is an outlier in model behavior, which is a different sign for how do you have an opinionated taste of your problem. So again, designers have not become less opinionated because AI has become better. In fact, they've become more opinionated because they realize they have more control over the output. I think in the same way, like I think many other functions, there will be people who have an opinion of what the right answer is that are going to be able to steer these models. I think also for adaptive AI, like typically a good outcome is that you care less about the weights, right? And so I actually think, the last 10 years, it's all been about the weights. What models released, what's the snap. And I actually hope in the future, you don't care about much about the weights. And in fact, like you care much more about the outcome for you. And like, did something work for you today? And I think that's an interesting shift as well.
Great. Thank you, Sarah. Well, right now we have a quick gift presentation and
Oh,
hopefully
exactly.
a good photo taking session before we move on to the networking sessions.
Okay,
Thank you.
excellent.
Thank you, Sarah.